Assalamu alaikum. Today is our fifth lecture of applications and methods of nuclear tracks. So, in this lecture, we will discuss basically the solid state nuclear track detection, which is so called as SSNDT. Okay, we will discuss about this. Okay, solid state nuclear tracks detection. In this, there is a criteria for tracks which is called criteria for track registration by nuclear etching. First of all, you must have to know what is basically the tracks, how we can visualize our nuclear tracks. So there is a criteria, there is a method so called as track visualization technique, and that technique is so called as etching. Okay, so then I will discuss in this lecture is basically our main thing, which is the primary ionization. Okay, which is known by symbol J. Okay, criterion, this is known as primary ionization criterion. Okay, and the formula for this is basically the parameter J representing the primary ionization rate, okay, or the density of radiation damage. Okay, this is basically function of Z and and beta, which you know that basically equals to V by C, and a functional form of based on this work of Bethe is usually can be written as by this formula J is, which is I already told you, basically the primary ionization rate, or you can say the density of radiation damage basically. Okay, this J is basically the density of radiation damage. You can write it here as, okay, and this formula is basically equals to A dot Z square E divided by beta square, bracket ln of beta square 1 minus beta square plus K minus beta minus delta beta. Okay, where Z, basically Z of E is basically the effective charge of the particle. Okay, effective charge, basically this is the charge number. Okay, effective, and you can see here a constant K, and A is also a constant, and these are basically the constants for a given medium. Okay, this depends upon medium to medium, whereas your delta B is basically the relativistic correction term. Okay, to account for the you can say polarization of the stopping medium, okay, by the electromagnetic field of the moving particle. Okay, so this beta is basically the relativistic correction, you can say. So this is basically the ionization potential, which I already know is basically the ionization primary ionization rate, or you can say it as the density of radiation damage. Okay, basically this equation accounts for all the etching rates, okay, measurements made for far, as I told you in this. Okay, how you can visualize your nuclear tracks by etching. So next, let us just took an example. I just took an example for you from the primary ionization. Basically the question is, an alpha particle is passing through a plastic detector. Now your particle is alpha, and now is passing through a plastic detector. Okay, when its velocity is beta equals to 0.8, and you know beta is basically equals to V by C. Okay, what you have to find, you have to find the primary ionization rate when K equals to 0.3, which is a constant, and A equals to 1.5 into 10 raised to power minus 14, which is also a constant, whereas delta B is equals to 0.02 beta. What you have to do, you have to find the primary ionization J. As you know, the formula for the primary ionization is basically A, which is given dot Z. Okay, because our alpha particle, and alpha particle, you know, its Z number is basically 2, so 2 here, and this E comes because of this E. Okay, and beta is also given, which you know 0.8. Okay, 0.8 square, ln of beta square divided by 1 minus beta square plus K value minus beta minus delta value. Delta value is already given, which is 0.02 beta, 0.02, and beta value is 0.08. After substituting and after calculating all these values, you will get your final expression for the J, or you can say the primary ionization or you can say the density of radiation damage is basically equals to 8.8 multiplied by 10 raised to power minus 34, and the unit of this primary ionization, or you can say that the damage, okay, radiation damage, is also joule per meter and in previous cases. Okay, so this is how you can find the primary ionization. Okay, now let's move further. Now our first next subtopic is radius restricted energy loss, which is the abbreviation of RREL. Okay, and now what is basically this restricted energy loss? Okay, uh, basically in radius restricted energy loss, basically it includes energy deposited. Okay, it includes energy deposited by all the events occurring within the radius r. Okay, because this is radius restricted. Okay, so we can say that events occurring within the radius r of the particle trajectory. Okay, whereas lr criterion gives importance to the track region. Okay, and attempts to consider only that part of the energy of gamma rays, okay, of delta rays basically. Okay, as we do in previously delta case. Okay, so in that case, what you can say that actually deposited in the core region, irrespective of the energy of the gamma rays, lr can be given by this formula. Okay, whereas lr is equals to L infinity. Okay, and what is this L infinity? Is basically the total rate of the energy loss, which you already know, dE by dx. Okay, stopping power, you can also know that the stopping power dE by dx. So basically L infinity is the total rate of energy loss. Okay, whereas now L infinity a z square effective divided by beta square ln of r by capital R by small r minus 1 minus small r by capital R, whereas capital R is basically the maximum track width. Okay, basically it's the track width of a particle, it's the maximum track width, and small a is basically the constant of the given medium or material, because it depends material to material. Every material have their own medium. Okay, so this small a is basically the constant of medium, okay, of material, and this small r is basically the radial distance from the particle trajectory. Okay, and adjustable parameter in this model. Okay, you can say that. So this is the radial distance from the particle trajectory. So this is the radius restricted energy loss, RREL. So you can find, if the question is given, you can find easily the restricted energy loss if you know this relationship between lr. Okay, so there is a practical problem for you to illustrate your subtopic perfectly, and that problem is basically: consider a proton is entered in CR39 detector and give restricted energy loss. Okay, whereas beta equals to 0.9 and r equals to 20 millimeter. Okay, this r, you know, that is basically the maximum track width. So maximum track width is given, and small r radial distance of the particle trajectory is also given, and that was 8 millimeter, while the constants a equals to 2.5 into 10 raised to power minus 4 meter per second square. Okay, also the L infinity, which you already know, basically the total rate of energy loss, is also given, and that is 4 multiplied 10 raised to power minus 3, and the unit of this L is also joule per meter. Okay, so you have to calculate the restricted energy loss, LR. Okay, so the same formula you can find easily. So LR is basically equals to L infinity, as it is the value of a z square divided by beta square. Okay, and multiplies by ln of capital R divided by small r, 20 divided by 5. Okay, minus 1 minus small r by capital R. After substituting all the values and calculating, you will get your final relationship for the radius restricted energy loss, and that was equals to 7.8 multiplies by 10 raised to power minus 7 joule per meter, because the unit of L infinity is also joule per meter. So you can say the unit of the energy restricted loss is also joule per meter square. So this is how you can find the RREL, radius restricted energy loss. Okay, so let's move towards the next topic. So our next topic is basically the critical angle of etching. Now, what is the actual meaning of critical angle of etching? You can see that there is a figure I illustrate here, that there are two paths, path 1, path 2. A charged particle is coming and entering into this trajectory, making an angle theta here, and it has a velocity of vt. Okay, and this the bulk velocity is basically noted by you can say vg. Okay, this is the upper surface, you can say basically the original surface of the bulk material. This, okay, this upper line is basically the original surface of the bulk material, and this lower line is basically the etch surface. Okay, after time t you etch this, and this is after. So vgt is basically the between the distance between these two, and theta is making the angle. Okay, so this is what basically the critical angle is. This basically assuming that the charge particle parameters and the detector characteristics are such that an etchable track can result its actual observation. Okay, so you can say its actual observation is influenced by a geometrical factor, and that is known as basically the critical angle of etching. So here you can say the track length, because as you know that the formula of distance s equals to vt, because there is also distance, so you can say that here also. Okay, so our track length, that is equals to vt dot t. Okay, for the case of bulk length, uppercase, again this is length, so it is become vgt. Okay, vg is the velocity and t is after some time. So you have to take a ratio, so taking ratio vt by vg, it's always greater than 1. So you can conclude that vt is always greater than vg, means your lower track velocity is always greater than the vg. Okay, vg bulk. Okay, upside. So this is, and then what you have to do, you have to, it's making an angle. So here cos angle equals to 0, only you will left with the sin theta angle, so it becomes vg dot t. Okay, vt dot t sin theta, which is equals to vgt. T cancels with the t. Now because we are concerning with the critical angle, and we have to find the critical angle, means we have to find angle theta, so we have to move sine theta, all other aspects on to the other side, and the sine theta becomes equals to vg by vt, because you know that vt, your lower path is greater than upper. Okay, so vt is always greater than vg, so sine theta is also equals to vg by vt. So then finding theta becomes equals to sine inverse of vg by dt. So this is basically the formula for critical angle of etching. So you can find easily if there is a problem. So I have also for this topic I have also a practical problem for you to illustrate this topic quite easy. Okay, so what's our problem is basically, suppose a nuclear particle passes through a solid state nuclear track. Now there is a nuclear particle that is traveling, passing through a solid state nuclear track. Detector means SL, SS and T. Okay, and the detector is aged for 60 minutes. So the time is given, and that is 60 minutes. Find the track etching rate. Now you have to find track etching rate, means VT. Okay, if the length of the track is 1.2 millimeter, so quite easy, length is given. Okay, means distance is given. Distance, s equals to vt, so means length basically l equals to vt. You have to find vt, means track etching rate. Okay, so v becomes equals to l by t. L value is given 1.2 into 10 raised to minus 3 meters. Okay, and time 60 minutes is given, and 60 minutes in seconds is basically equals to 3600 seconds. So after calculating, you will get your tracking etching rate Vt is equals to 3.3 multiplies by 10 raised to a minus 7 because it's velocity, so the unit is meter per second. Okay. So last problem of today's lecture is basically you can see the problem is if the bulk etching rate Vg. Now in this problem the bulk etching rate is given Vg, which is equals to 0.05 millimeter per minute. Okay. And the track etching rate now also given, and that is basically 0.02 millimeter per minute. Okay. You have to calculate the critical angle. You already know the formula for the case of critical angle, and that is equals to theta equals to sine inverse of Vg by Vt, and you know the value of Vg is 0.05, and you know the value for the Vt is basically 0.02. After putting theta equals to sine inverse of 0.05 divided by 0.02, you will get your final relation, and that is equals to 14.4 degree. So this is how you can find the critical angle and how you can find the bulk etching. Vg you can easily find, and you can find easily tracked etching rate as we did in previous numerical. Okay, so this is our lecture number 5 of working principles and applications of nuclear tracks. Okay, this is our lecture number 5, and we all did. So in this lecture basically we did the primary ionization, we did the track visualization technique, then we discussed radius restricted energy loss, RREL, then finally we discussed critical angle of etching. So that's all for today for lecture number 5. Thanks for watching. Allah Hafiz.